I will begin with a word of prayer once I get up here. Dearly Father, we thank you for this day again. I thank you for these students, this class, and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So let me give you a ridiculous example that is kind of like one of these problems on your mission. All right? So here we go. Example 1. I tried to work one of these in earlier, but I forgot to until just now. But suppose that you have the sixth derivative of y with respect to x plus 15 times the fifth derivative of y with respect to x plus 96 times the fourth derivative of y with respect to x plus 254 the third derivative of y with respect to x, and minus 3 times the second derivative of y with respect to x, minus 1425 dy dx, minus 1250 equals 0. And, yeah.
Is that 255 or 225y?
250.
For d cubed?
Yes, thank you. There's a y there. Very good. X.
Talking about the fourth determinant, the 25y.
That was supposed to be 254, but I seem to have. I wonder what else I've done. Let's take a look back. 15, 96, 254, minus 3, 1425, 12. All right, very good. And here's the hint that this comes with. Hint. Y equals x times e to the minus 4x cosine of 3x is a solution. Solve it. All right, so in some sense, this one's a little bit worse than the one I gave you on the on your surprise stack mission, right? So you guys tell me, like, if this is present in the solution set, what does that tell you about if I was to rewrite this monstrosity as, L acting on y is equal to 0, right? What does that tell you about L? It has to have imaginary root somewhere, right? This comes from what? This comes from lambda is equal to like minus 4 plus or minus 3i repeated, right? That's how you get this x here. There's not just a complex pair of roots, there has to be a repeated pair of complex roots in order to get that kind of solution. So we just work backwards, you see? This is coming from d plus 4 quantity squared plus 9 squared. All right? Which, if we multiply that out, we've got d squared plus 8d plus 25, I think. 16 plus 9. Is that 25? Yeah, 25. But I got to square that thing, right? It's actually it's a quartic operator that we're gifted. This hint is huge. It's a huge hint. It gives you like a lot of the L. But I have to multiply this out, right? So, all right, great, we can do that. That's just algebra. So I've got like a, d to the fourth. I'm just going to do it and then collect things. So I got d to the fourth plus 8d cubed plus 25d squared plus 8d cubed plus 64d squared plus, thank you, 200d plus 25d squared plus 200d plus 625. All right. But of course we can collect some things together. That's d to the fourth, 16d cubed $114, is that right? I think 50 plus 64 is 114. I got 400 derivatives in here, 400d, and plus 625. Okay, great. All right. So formally, I'm trying to, what do I want to do? I mean, I know that L, right, is equal to something, right, times this thing, d to the fourth plus 16d cubed plus 114d squared. If you see an error, now would be the time to tell me about it. 400d plus 625. And what goes over here? Polynomial division, very good. Can you tell me some of that without doing that, though? I mean, this is a what? This has got to be quadratic, right? Because it's sixth order. So like L is equal to, you can see it just from looking at it, L is d to the sixth plus stuff, right? Minus 1250, yeah? How do we get 1250, minus 1250 from 625? Oh, minus 2. So that's for free. And other things for free, right? I mean, obviously there's got to be a d squared here, right? In order to have this times that and give me this one, right? But yeah, this part in the middle, you might be able to see it, but let's look at a technique. So the technique is this. We've got d to the sixth plus 15 d to the fifth plus 96 d to the fourth plus 254 d cubed minus 3d squared minus 1425 d minus 1250. And I am trying to divide into that sixth order polynomial this quartic factor. Right? If we can work that out, then guess what? We have found the mystery, the missing piece, which one of you already guessed correctly. We'll find out, won't we? So it's long division. It's easy enough to start. What's what?
I was trying to see what that middle term would be.
Oh, yeah, let's work it out. That's what we're doing. So d to the fourth goes, d squared goes here, right? Because d squared times d to the fourth, so that gives me a d to the sixth plus 16 d to the fifth plus 114 d to the fourth plus 400 d cubed plus 625 d squared. So you take that and subtract it. Lo and behold, you get minus d to the fifth. What's 114? What's that? Minus 18. D to the fourth. Minus what? 156 d cubed. I hope you're right.
That was 46.
146.
146, huh? There was such derision in the correction to the arithmetic just now. It was, I could feel it. I could feel it. It had a certain rawness to it. I like it. 622. 622. Okay. Minus or minus 622?
No. Plus 622. No.
I think minus. Oh, wait a minute. Minus a minus.
Plus, yeah, 8.
That's right. That's what I'm. There we go.
This is why we lose points.
Minus 1425d minus 1250. All right. So what comes next? Apparently. To get from here to here, I minus d. And that gives me a minus d to the fifth, minus 16 d to the fourth, minus 114 d squared, d cubed, minus 400 d squared, minus 625d. Then subtract this thing.
So, quick question, is it possible that this could come out to anything but, if we already have our two guesses there, right? We know our squared term, we know our constant term.
Oh yes, but if this goes badly, then you did something else wrong.
That's true.
So it's a redundancy.
Right.
I mean, you're right. But this, if this works out also, then it gives you a greater confidence that. But yes, in the pressure of time, like on the test or something, you could bail right here and just, yeah, sure. Minus 32.
Yeah.
Minus 228. Minus 800. Plus 1250. Well, minus 1250 rather, right? All right. So finally, that's... Oh, come on. Wait a minute, what? Wait, what? Hey, what? Oh, wait a minute, I can't multiply. 2. So 2 times 16 is 32. 2 times 114 is 228. 2 times 400 is 800. 2 times... Okay, we're good. We're good. But I need a minus 2, right? Because... Oh, look, this is right here a mistake, right? Should be minus. Yeah, got to be careful. All right, so... Anyway, listen. This technique doesn't have to be this hard. I just made up this example to try to make it maximally painful, right? I think what you have in your homework is a little bit easier than this in some sense. It's harder in another sense because in the homework I gave you information which I think implies the existence of a quadratic factor maybe. So I think you're left over with like a quartic. I think in your homework this thing's quartic, whereas this thing's quadratic, if I remember right. Anyway, great. So what does this all tell us? So now we have learned that we're looking at L of y equals to 0, which actually has the form d. Well, what's d squared? D squared minus. Let me do this separate. D squared minus d minus 2 is d plus 2 times d minus 1, right? Wait a minute. Flip the script on that, right? D minus 2 plus 1, because the minus wins there. All right, so apparently we have d minus 2 times d plus 1 times this monstrosity, d plus 4 squared plus 9, all squared, acting on y equals to 0. This is, in fact, the true nature of the beast I asked you to solve, right? Once you factor the differential operator in this way, if you can, then you're pretty much home free, right? All you have to do is write down the answer. In fact, you could have written down 2/3 of the answer just from the hint alone, right? Like it was already clear as soon as I told you that x, what was the solution? Once I tell you x e to the minus 4x cosine 3x is solution, it should be immediately obvious to you that we have e to the minus 4x cosine 3x and c2 e to the 4. Did I say 4? I meant minus 4. Minus 4x sine 3x, right? These come along. If you meet, x e to the minus 4x cosine of 3x in a dark alley, beware, he comes with a posse. He's got there's three thugs in the shadows lurking beside him. They always coming together. They're all there in the solution set. You can see here. So that was this. I could have told you without any of the calculation over there, just from the hint alone, right? Because where there's x e to the minus 4x cosine of 3x, there has to be the rest of this in the general solution. But now that we figured out that other piece, we've got plus c5 e to the 2x plus c6 e to the minus x, and that's it. So there you go. That's the solution to my most extravagant constant coefficient problem we've worked this semester. All right. I'm not sure if I know any way to make it worse than this. This may be the worst version of this problem. I don't know. I think. Another thing I talked about in the homework that we haven't quite hit in class yet, but we should, is the idea of an integral solution. What does it mean to look for an integral solution to a problem? Mathematicians are very unimaginative in terms of their labeling. An integral solution is a solution that's written in terms of an integral. And that is very welcome news to be asked such a thing, because that means that you don't actually have to do the integral. You can leave it symbolic, right? So a good example of this, I'll do a quick one. If we had, y prime prime minus, let's say 9y equal to, let's say g of t, all right? And if I want to find the integral solution to this problem, the first order of business is to write down the fundamental solution set. So you guys tell me, what's the fundamental solution set to this problem? Dr. Joseph was just telling me about students taking his first test in this class. He had some disturbing tales. No one here is going to, well, anyway, I won't repeat. I heard things. You guys are better than that, though. This is fine. It's going to be okay in here. It's going to be okay. So how about this? We have what? Lambda squared minus 9 equals to 0. So lambda plus 3, lambda minus 3 equals to 0. However you want to see it, we have plus or minus 3, right? So what's my fundamental solution set? I got y1 is like e to the 3x, and y2 is e to the minus 3x, right? Right or wrong? Well, if I'm asking the question, it's obviously wrong. Why is it wrong? What's the independent variable in this problem? the primes don't tell you, but the g of t does. T is the independent variable here, so I should be writing t. All right? It's easy enough to miss, but this is an important step in any differential equations problem, is to identify what is the notation you're being asked to use, which is the independent variable. In some sense, it doesn't really matter because it's the same mathematics, but it does bug me when I see a mix of x's and t's in an answer. And as such, I take off points because I'm a petty, sad man with nothing else to do but take away your points. It's the only thing that gives me true happiness in my life at this point, to take away the points of... Okay, this isn't really true. I love my family, and I actually do like teaching you guys real stuff, but you got to find some kind of solace in grading. If anyone truly enjoys grading, there's something deeply, deeply wrong with that person. Anyway, so the variation of parameters, right? What does it say? Let us remember or learn it for the first time if you don't know already. Yp is v1y1 plus v2y2. This solves, L of y equals to g, where L of y1 is equal to 0, and L of y2 is equal to 0. And we are assuming y1 and y2 are linearly independent. All right, so we already have that. Linear independence of e to the 3t and e to the minus 3t. This is true. All right, and they are solutions to the homogeneous problem. There's a little bit more here, though. Provided v1 is equal to something, an integral, and v2 is equal to a different integral. They both involve g, because g is what makes it what it is. And they both have division by the Wronskian of y1 and y2, namely y1, y2 prime minus y2, y1 prime, y1, y2 prime minus y1, y2, y1 prime. Again, that's the Wronskian of y1, y2. And the funny thing is, essentially by Kramer's rule, there ends up being, if I remember right, minus y2 here and y1 here. And, depending on what the variable is here, if this is g of t, then I have to do an integral over dt, all right? Now, I doubt myself a little bit. So did you guys, any of you remember or have written down on your formula card the formula for variation of parameters? Anybody?
I have not.
You have, well, I don't know if it's right or not yet, so you're kind of getting ahead of the game. I'm assuming I remembered it right, 50-50. Sounds like you're great. It's kind of dark. Let's see here. So the formulas I'm talking about are on page 96 of my notes. And V1 is minus F times Y2. The F is the G in my, yeah, we're good. Yep, that's it. Now, I got to be careful. Generally speaking, there's a 1 over A. Generally speaking, there's an A down here. I forget about that because I usually make it so that so like L is equal to A d squared plus BD plus C in this context. So like this is the leading coefficient of the operator that defines this second order differential equation. But for us, A is what? A is just 1, right? So like, all right, so let's put it together. So variation of parameters. Now, not everybody teaches this way. Like some people make you work out the formulas for V1 and V2 every time you do this problem. And there probably is something to be gained there in terms of like some kind of redundancy check, much like there is for the integrating factor method, but I just don't do that. So I'm willing to use these formulas. Admittedly, that is a little bit, what's the word, hypocritical, given my stance on integrating factor method. Y2, so I've got, e to the minus 3t, and g of t, dt, divided by what? Let's work out y1, y2 prime, minus y1, y2, y1 prime, yeah? What does that work out to? Ooh. Ooh. Hey, look at that. What's that? It's what? What happens when e to the 3t and e to the minus 3t, meet on the sidewalk? They become 1. Let's see here. They go to 0 now. Well, e to the 0, which is 1, yeah. But you've got a minus 3 and a minus 3, so minus 6, right? So lo and behold, minus 6 is the denominator here. But I got to be careful. I'm supposed to put a minus here, right? So don't forget that minus. That goes here. So those cancel. And V2 is the integral of e to the 3t for us, g of t dt divided by minus 6. All right, let's put it all together. Y is equal to, let's see here, e to the 3t times v1, which is this. Let me bring the, I'll leave this, I don't know, would you guys want me to bring the 6 in or out of the integral? Let me bring it out. It's just, I feel like it belongs outside. 1/6 there. E to the minus 3t g of t dt plus, I guess I could do minus, right? Pull the minus out too. Minus 1/6 e to the minus 3t z integral of e to the 3t g of t dt. And there you go. That is the integral solution to this problem. Notice that if we take these integrals to be indefinite, and in other words, there is a constant added, what happens as you add the constant in the integration? What happens if you think about this one, like plus C1, and this one, plus 6C1, and plus minus 6C2 for your constants. What does that produce? It produces a C1, e to the 3t, and a C2, e to the minus 3t. So what I'm trying to tell you is the homogeneous solution's already in here in the sense that we take these integrals to be indefinite. So this is the general solution, which is also an integral solution here. Do you want me to work another one of these? Let's do another one of these, but this time Cauchy-Euler. What's the difference then? Let's see here. How about x squared y prime prime plus xy prime equals to, plus, I don't know. I reserve the right to change what we're putting over here. So this gives me a what? An r times r minus 1 plus r which would give me a r squared, but I want to make this more fun, so let's do like plus 16 y equals to g. That's pretty interesting. So when I look at the characteristic equation of the Cauchy-Euler problem, I have r times r minus 1 from this piece, I've got r from that piece, and then I get plus 16 here, right? And so this gives me an r squared. The r's be canceling, r plus 16 equals to 0, which tells me that my r is plus or minus 4i. What's the fundamental solution set in this context? Oh, lest I forget again, this is a twofer. You can check 2 boxes. It's very exciting, yes. If you also count top hat, we've taken attendance 3 times today. That's 3 times the attendance goodness you get in any other class here. You know, think of it. You're welcome. Okay. Also, I never take points off for attendance in the end, so like, whatever. Okay, so this means that we think about like the complex solution, z equals, you know, x to the 4i, but I understand that to mean cosine of the natural log of 4 times x plus I times the sine of the natural log of 4 times x, if I remember it right. Yeah. So in this context, y1 is what? y1 is cosine of 4 natural log of x. Oh, wait a minute. Did I? Ooh, my bad. Let me just do my formal heuristic here for a second. This is exponential of the natural log of x to the 4i, which suggests to me exponential of 4i natural log of x, which does not suggest what I wrote. It suggests 4 log x for the cosine and the sine of 4 log x. Not natural log of 4. That was nonsense. So the cosine of 4 times the natural log of x for my y1, and for my y2, we will have the sine of 4 times the natural log of x. All right? We should probably calculate the Wronskian. Get that out of the way, right? So what's the Wronskian here? Y1, y2 prime minus y2, y1 prime. What's that work out to here? So like y1 is, so we've got, you know, cosine squared of 4 log x times, well, apparently 4 over x, right? And then minus sine, minus and minus is plus, so plus sine squared 4 log x times 4 over x. So double check me on that. The y1 prime is a cosine derivative, which gives me a minus, and the minus and minus gives me a plus. And I got a cosine squared plus sine squared, 1. So lo and behold, the Wronskian works out to 4 over x. All right? So then, my v1 is the integral of minus y2 times g divided by a times, you know, y1, y2 prime minus y2, y1 prime. Right? In this case, dx or dt? Dx this time, right? X is the independent variable in this example. All right, great. And then this is the integral. Y2 was, so minus the sine of 4 times the log of x times g of x, all divided by x. What's a? See? A, in this case, is x squared. right? Now you might wonder, wait a minute, what if you divided this equation by x squared? What would happen then? What happens if you divide the equation by x squared? Where does the x squared go? It goes to the right. It divides g. What happens to the formula? Then the 1 over x squared gets picked up in terms of the new g. So it's going to be in there, whether or not you divide the equation by x squared at the start or not. But here it is, x squared. And the Wronskian is 4 over x. All right? And my V2, the integral of y1g divided by a times the Wronskian. I'm starting to feel like I should have called that w, And that's the integral of cosine of 4 times the natural log of x times my g of x dx, all divided by x squared times, well, again, 4 over x. All right. Let's put it all together. General solution then, again, this is an integral solution, is the following. y1 is cosine of 4 times the natural log of x. And then you got the integral of, minus sine of 4 log x times g of x dx divided by 4x, I guess, right? And then plus the sine of 4 times natural log of x, the integral of the cosine of 4 log x times g of x dx, all divided by, 4x. And there you have it. That is the integral solution to this problem, all right? And there's a problem in your surprise attack mission, which is, I think it's pretty similar to this in terms of its nature. I hope I haven't done exactly the same problem. I hope you're studying the problems in the practice mission, right? There's a wealth of examples there. Some of them may be very relevant to your current surprise attack mission. I mean, very, very relevant. I hope I can be clear enough about that. Anyway. Do not write, the answer is blah, see surprise, see practice mission solution. I actually do want you to work through it, all right? But anyway. Any questions? All right. Well, with that, I'm going to turn to a different topic now. Something that's very, very different. And the topic is what's known as differential forms. And so differential forms are objects which you've dabbled with them in calculus. You talk about the total differential of a, what's the word? Function, right? And the total differential of a function, what does it give you? Do you guys remember? Like, if I have f is a function of x, y, and z, what's a df? df is what? It's, partial f, partial x, dx, right? Partial f, partial y, dy, plus partial f, partial z, dz. Now you might have just thought of that as a formal heuristic for remembering a particular approximation procedure, and indeed you could think of it that way. That is what calculus books peddle. But it's much more than that, actually, because it's the first chapter in a much deeper story, namely the story of the exterior calculus. The exterior calculus is the calculus which we can do on a curved space of arbitrary dimension. We replace curl, divergence, things like that, with one sweeping notion of the exterior derivative. This is the first instance of the exterior derivative. This is what's called a zero form. The reason it's called a zero form is it has no differentials. On the other hand, this right here, this is a one form. Why? Because it has one differential. All right? So, wait a minute. So could we take another derivative? What if we had, let's say alpha is a dx plus b dy plus c dz, right? That's a one form. So what I'm going to introduce you to is the idea is that we can differentiate that with what's called the exterior derivative, and in so doing produce a two form. So d alpha, and this is just the definition, guys, is dA wedge dx plus dB wedge dy plus dC wedge dz. Now what is this dA and dB and dC? Well, that's the total differential that you already know from calculus 3, you see. So like dA is nothing more than partial x of a dx plus, partial y of a dy plus partial z of a dz. Oy, wedged with dx. And then I have the b derivatives, like partial x of b dx plus partial y of b dy plus partial z of b dz. That gets wedged with the dy. And then finally plus the c derivatives, so like partial x of c dx plus partial y of c dy plus partial z of c dz wedged with the dz. Now let me tell you the story of how the wedge product works. The wedge product is a new algebra, and in a summary, I can show you how it works really briefly. Basically, these are the rules that govern it. The rules that govern it are this: dx wedge dx is 0, dy wedge dy is 0, and dz wedge dz is 0. So subject to those rules, you see, there's three terms here that are vanishing. Because the way the wedge product works is it also obeys the usual laws of algebra. So like as I take this x and I wedge with that x, this piece is gone. All right? I take this y, I wedge with that y, that piece is gone. I take this z, I wedge with that z, that piece is gone. What remains, you see, is this. And the other thing I should mention is dy wedge dx is minus dx wedge dy. Dy wedge dz is minus dz wedge dy. And finally, dx wedge dz is minus dz wedge dx. So like like the cross product, right? It's a lot like the cross product. So with that in mind, I can rewrite this, you see, as something times dz wedge dx plus something else times, let us say, dx wedge dy plus something else. These are kind of out of order from my preference, but I'm gonna do. My bad. Let me switch this around. I'm gonna do yz here. I'm gonna put the yz terms first, and then I'm gonna put the dz wedge dx terms here, and then I'm gonna put the dx wedge dy terms over here, right? And so what you're looking at, all right, is, all right, so where's my yz? I've got, see, partial a partial y minus partial b partial x. I think. Wait, no. Hold on a second. This is coming from, I'm looking for yz. So minus partial b partial z, I should say. Yz, this one, partial c, it was partial c partial y I should have had. Partial c, right here, partial c partial y. All right, this term here, and this term over here, right? Those are the first two. Next up, with zx, I've got this one. So I've got partial a partial z minus, I believe it's partial c partial x. Where's that one? See this right here? Why is there a minus? Do you guys understand? Because dx wedge dz, I have to switch them around. And in so doing, I put the minus here. All right. And last but not least there, we have partial b partial x minus partial a partial y, I believe. Yeah, see this one over here? That gives me this one. All right, so let me suggest some notation, guys. So omega subvector ABC is a dx plus b dy plus c dz. And big phi of ABC is equal to a times dy wedge dz plus b dz wedge dx plus c dx wedge dy. These are what are known respectively as the flux, the work form, and this guy is the flux form. A fundamental identity you can prove is this, guys. If I take omega a vector wedged with omega b vector, guess what it gives you? So the wedge product of two one forms is a two form. The two form, which two form though? It is exactly the two form that corresponds to the cross product. So this, in this way, the wedge product encodes the cross product. With this notation I've just introduced, can you tell me another way to look at this? This says that df is actually what? It's the work form of what vector field? What's that?
X, Y, Z.
What vector field? This is A is partial f, partial x, B is partial f, partial y, C is partial f, partial z. This is the gradient vector field. So this is the work form of nabla f. The exterior derivative naturally reproduces the gradient at the lowest level. The next level up here, if you take this calculation and you understand it properly, what you can see here is that the exterior derivative of the work form of f is equal to the flux form of what? If my f is ABC, you guys tell me, end of Calc 3, I know it's a little fuzzy, but do you remember what we did at the end of Calc 3? We did divergence, curl, gradient. Which is this? Difference of derivatives of not the same component, right? This is the z component, y differentiated. This is the y component, z differentiated. This is the x component, z differentiated. The z component, x differentiated. The y component, x differentiated. The x component, y differentiated. That's the curl. So this is, in fact, this calculation shows you that the exterior derivative of the work form gives you the flux form of the curl. So next class, I'll show you the next chapter in this, which is what happens when you exterior differentiate a two form. What do you think happens? You're going to get three form. What derivative is that going to pick up on? We saw gradient. We saw curl. What's next? the next thing is the divergence. So anyway, I'll stop here for today, guys. Don't forget to bring your stuff next time, yeah?